Okay, so for the second academic lecture for this afternoon, the title of the presentation is Introduction to Single Stage Object Detection. The topic will discuss single stage object detection, which is a cornerstone in modern computer vision due to their balance of speed and accuracy. If you're familiar with the YOLO architecture, that is a single stage object detection model. Unlike traditional two-stage detectors that separate region proposal and classification, single stage detectors perform object localization and classification in one pass, making them highly efficient for real-time applications. The lecture that will be given to us by Ryan will provide a comprehensive introduction to single-stage object detection, covering the fundamental principles, popular architectures such as SSD, RetinaNet, and YOLO, as well as recent improvements in anchor-free methods. Attendees will gain insight into the design and trade-off between speed and accuracy, evaluation metrics, and the different practical use cases in both industry and research. So that would be the uh, content of this lecture. And let me introduce to you the speaker. Your speaker for this lecture would be Matthew Ryan Karandang. We call him Ryan in the lab. He is an undergraduate student at DLSU University, pursuing a degree in computer science as part of the honors program or the BSMSCS program. Currently, he is conducting his thesis research on single-stage object detection, specifically developing a module to enhance a model's performance for vehicle detection. So I'm now giving the floor to Ryan. Ryan, you may start your presentation.
Okay, so thank you, Sir Aaron, for that wonderful introduction. So once again, I'm Matthew Ryan Karandang, and I will be presenting my lecture titled Single Stage, which is exploring single stage object detection. So here is a quick roadmap for the lecture for today. So we'll start with the foundational definition of object detection. Then we'll introduce the concept of single stage object detectors. And then we'll be contrasting them with two-stage object detection. From there, we'll be tackling then different architectures in single-stage object detection. And then advantages, disadvantages, as well as its use cases and applications in real-time systems. So let's start from the beginning. So object detection at its core is a computer vision tasks that basically answers two questions. So the two questions are what are the objects that are in the image and where are those objects? So this image here is a perfect example of what object detection does. So as you can see here, it's a busy street with different objects. So uh, the model it was trained to detect different cars in the image. So first of all, it was able to classify them. Basically, the red boxes would be cars that are facing forward, and the green boxes would be cars that are facing backward. So it was able to classify them, and it was certainly able to locate them since the model was able to draw bounding boxes around them. So, as noted by Son and colleagues in a 2024 paper, advancements in deep learnings have been a driving force here. There are new algorithms that can understand complex features at different scales, which allows them to succeed in complex real-world scenes like the image shows above. So, as we can see here, so here is the evolution of or the timeline of object detection. So first, we're going to start off with the Viola-Jones detector and HOG plus SVM. So both of these are quote unquote classical object detection. So Viola-Jones detector is actually a face recognition detection. So classical in this context means that uh, they actually look for, or they're programmed to look for certain features in a face, or they're programmed to look for certain facial features. So for example, in Viola-Jones detector, they actually distinguish faces through the position of eyebrows or foreheads, rather than them being fed multiple or millions of data and learning from there. So it's technically, let's say, hard-coded in a way. It's rule-based learning, so rules are actually programmed into these models. Uh, then we have AlexNet 2012. This is actually uh, one of the notable architectures, since it's actually the model that has proved to be has proved that convolutional neural networks are quite efficient in computer vision tasks. And from there on, there's a trend that after AlexNet, it would be mostly convolutional neural networks, with the exception of vision transformers. So RCNN, which would be the next, is a two-stage deep learning detector, and then followed by that, there are iterations of fast and faster RCNN. And the main focus of this topic would be the introduction of YOLO and SSD as well, which are uh, the birth of single stage object detectors. And then from 2017 onwards, there have been different iterations of the said architecture, with uh, also efficient depth coming into play, that is developed by Google, and different vision transformers that are completely different architecture. But for this lecture, we'll be focusing on single stage object detectors. So I mentioned single stage object detectors a lot. So what exactly are they? So single stage detectors, as the name implies, it identifies and locates yung objects in an image in a single unified step. Looking at this image, the model isn't looking for people, then looking for bikes, and then looking for buildings. It's looking at the entire image. It's looking at the entire image, and or the whole scene, and predicting all of these boxes and labels simultaneously. So, which makes it fast and reliable, for real-time applications. This comes at a cost, however, since with higher speed comes at the cost of precision. So moving on. So here's the, I guess, general idea of single stage detector. So first we have is the input image, and then from there it's gonna be passed to the backbone of the network. So the backbone will extract these features from the image, so it's gonna generate different feature maps. So as explained earlier, feature maps are like uh the features of an image. So like, as an example would be its texture, its the different lines, contours that are present in the image. And then from there, it's gonna be passed to two fully connected layers. One is the classes. One would predict the class, and one would predict the bounding boxes. So classes here, it has a softmax function. So a softmax would mean that for every class, it will predict the probability of it. So let's say, for example, we're gonna have two classes. So first we have is a car and a bike. So a softmax function, what a softmax function does is it will predict the probability of that class, of an object, to certain classes. So it's gonna have an output of, let's say, 90% a bike and 10% of an object, as an example. So yeah, it's basically for predicting classes. For bounding boxes, its task is to locate where the image is. So basically, the position of the position of the object in the image. So it's gonna have It's going to predict the XY coordinates and as well as the height and width of the box itself. So how do these single stage object detectors differ from two-stage detectors? So first, two-stage detectors uh, is a type of computer vision model that identifies and locates objects in an image first by proposing candidate regions and then classifying and refining each region. So this design allows them to achieve higher localization accuracy, but often at the cost of being more computationally expensive. So from there alone, you can tell that, let's say, an image filled with different objects is filled with different objects is fed into the network. Single stage object detectors would first go through a separate network, which would uh, propose regions of interest. So regions of interest would mean that the network would propose these regions to since that these regions might have an object in it. So it might have an object or it might not have an object. It depends on the network. So from there alone, you can see how single stage object detectors would be more faster since single stage object detectors immediately goes into the prediction stage of wherein it takes the features and it already identifies the classes and the bounding boxes of each object of the entire image, while two-stage object detectors would take the features and still go through another network wherein they would be they would be uh where the regions of interest would be projected, and then from there will be the predictions made. So this would be clearer in the next slide, which we have here. So the one above is one stage object detection. So first we have is the backbone. So this would be generating your features for the image, your different feature maps and such. And from there, it goes immediately to the regression box, which will produce the location or the bounding boxes of that image, and the classification box, which will be uh, identifying its class. For two-stage object detection, however, the features would go through an object proposal. So this would mean that uh, each object proposal in this case would eventually also have separate predictions, which is also adds up to why it's a lot slower than single stage object detection, as well as since it's gonna have different region proposals, so it's gonna be a lot slower since it has to go through a different set of networks in order for it to actually propose different regions that might contain an image. So here we have is a more I guess defined different distinguishes between differences between the two. So first we have is the backbone. So there's really no difference in the backbone since it's already gathering its features. It's only gathering the features of the different images. But as we can see here above, we have is the two-stage object detector. So the features go into region of interest pooling as well as another set of networks that proposes a proposes a region of interest at where an object might be. So from there, it after the proposal, it will then do its final prediction and wherein it's gonna be identifying its class and location. Compare that to single stage object detectors, wherein the features directly go into the region of interest pooling, which will then already have predictions for the entire image. So with with the with that distinguishing the difference between single stage and two-stage detectors, we're gonna be moving on to the different single stage architectures that are quite prominent in the field. Starting off with, I guess, the one of the most notable and highly highly sought after, which is the YOLO architecture. So the YOLO stands for you only look once, and as the name perfectly describes, um, it does single passes to each image. So the original 2016 paper by Redmond and colleagues was re- revolutionary. So it frames object detection not as a complex pipeline, but as a single regression problem. So it takes the entire image, passes it through the network once, and directly predicts all the bounding boxes and their class probabilities. So this design is what allows it to achieve real-time performance. But as the authors noted, this speed came at a cost of making more localization errors, meaning that boxes weren't always perfectly aligned. Uh, so here is the original YOLO architecture. I believe this is the, yeah, so this is the first YOLO architecture, YOLO V1. So it might look complex, but the important thing to notice that is this a single continuous network. So basically from left to right, from the further leftmost box, it would be the input of the image. So as a 448 by 448 image. Then each convolutional layer will be extracting extracting features from the images, and then the max pool layer would basically reduce the size of the input for the next convolutional layer. So as the uh as the image goes further and further to the network, you start to gain more and more features about that image. And then finally, for the fully connected layer, that would mean that it would be the prediction layer, where the prediction where the feature maps are taken and made predictions, such as for the class and the where it is located for the bounding boxes. So here we have is this diagram explains the general concept behind YOLO. So first, it divides the input image into an S by S grid shown on the left. So each grid is responsible for predicting any object whose center falls inside of it. For every cell, the network predicts both the bounding boxes and the class probabilities. And then when you put all those raw predictions together, you get a messy image, which is basically the top middle. But after then it gets filtered by non-max suppression, which we'll get into later. And it combines both the class probability map and the bounding boxes and confidence to make its final detections. So moving on. So here's a more of modern YOLO architecture. So I believe this is YOLO V12. So we're not gonna be diving in too much detail into this architecture since it's an introductory lecture. So what I just wanted to show here was that there have been different innovations when it comes to the YOLO architecture, with it starting from a single and simple network be and eventually evolving into a quite complex but fairly simple still of an architecture. So basically what we have here are, generally this is the backbone. So basically this extract features from the image itself, and then as it extract features after the feature maps are generated, it goes into the neck. So the neck here is it recombines the feature maps from the backbone. So notice the upsample and concat blocks. It takes high resolution features, which is good for small objects, and low resolution features that is good for context, and fuses them together. So this allows the network to to detect both small and large objects effectively. So this basically removes the bias of if you have larger or smaller objects, since larger objects tend to have more pixels. So uh, the the model might have a bias towards larger objects. So having the neck here basically not only removes that bias, but improves the model's detection for smaller and larger images. And finally, we have the detection head. Since YOLO V12 also have different uh, use cases, it also has segmentation, that object detection and whatnot. It has different segmentation. It has different heads, such as detection heads, segmentation heads, and class heads. So moving on to the second architecture, we have SSD, or single shot multi-box detector. So this was published back in 2016, around the same time as the first YOLO. So SSD's key idea was to tackle the problem of objects at different scales. So its design uses a set of default bounding boxes, which we'll see later. But you can think of them as a predefined template or anchors at different scales and aspect ratios. So it places these default boxes across multiple feature maps. So as we'll see, is what allows to get both high speed and good accuracy. So here is the overall architecture of the SSD. So as we can see here, the main difference with its YOLO is that as it's going through its backbone, which in this case is VGG16, uh, it's already getting its feature maps from different layers of the backbone and being sent into the detection head. So what we can see here is that convolutional 4_3 would send their feature maps directly to the detection head, as well as convolution 7 and convolution 8_2 and convolution 9_2, and so on and so forth. So uh each layer of the backbone sends their feature maps to the detection head. Uh and all these predictions are gathered and then filtered using non-maximum suppression to get the final and clean result. So non-maximum suppression would be, it just since there are a lot of predictions in this case, since there are a lot of feature maps that are being combined, and a lot of bounding boxes are tend to overlap. Non-maximum suppression basically just means that overlapping bounding boxes have different confidences. So non-maximum suppression does is uh, it basically selects the best bounding boxes that has the best confidence. So let's say, for example, we have a picture with that has an object in it, and that object has let's say 10 different bounding boxes. And for those 10 different bounding boxes, not all of them would have the same confidence as none not all of them will have the same confidence. So non-maximum suppression uh, helps in reducing those overlapping bounding boxes to that certain object, since it will only select the best one out of those overlapping bounding boxes and remove the other 9 bounding boxes. So that's basically what it does. So here we have is the SSD architecture side by side with the YOLO diagram. So first, YOLO V1 predicted from one final feature map. SSD predicts from multiple feature maps at the different scales. So as we can see here, um, this is the backbone of SSD as well. And it takes different features from different layers of the backbone. While the YOLO architecture only takes the feature maps from the final layer of its backbone. So that's basically the difference between SSD and the YOLO architecture. Then we have is what's called efficient depth. So efficient depth So efficient depth is a scalable one-stage object detector designed to optimize for both accuracy and efficiency. So its design introduces two key innovations, a weighted bidirectional feature pyramid network, or BiFPN, and for better multi-scale feature fusion, and a compound scaling method that uniformly scales the backbone, feature network, and prediction networks resolution, depth, and width. Mo- So here is the architecture. So this diagram shows the architecture of efficient depth. So the back efficient depths, it uses the backbone uses a highly efficient uh it's a highly efficient backbone to get feature maps at different scales. So it basically uh just like before, it reduces the input of each layer. But like SSD, it's also getting feature maps from different layers of the backbone. So as we can see here, between P3 and P4, the feature maps get sent to the neck itself, which we'll talk about in a while. Between P4 and P5, the feature maps will also be used in the neck, and so on and so forth. So that's the idea. But the main contribution of efficient depth is the BiFPN layer, which is the middle or the neck. So this is it is an advanced neck called bidirectional feature pyramid network, or just BiFPN. So looking at the arrows, it doesn't just combine features in one direction. It has arrows going both up and down. Plus, it also skips connections. So as we can see here, skip connections that go from the original backbone directly to the fusion layers, which is right here. So this is so basically this allows for a much richer and faster feature mixing. So they're basically mixing different features from different layers. Uh the main difference between this and SSD would be that SSD just combines all the features at once, while this is a more let's say it's a more there's a more distinction between which layers should be combined and whatnot. So here's a more here's another example of its architecture. So here we have is the input image. So from the efficient net backbone, we're gonna be taking features from different layers of the different layers of the backbone itself, and then from there it's gonna have n by FPN layers. It's stated here as n since we can actually have the user can actually make state or declare how many by FPN layers we have. But uh, as you can see, that increasing more by FPN layers would mean more computational power, and that would mean it would result in a much slower prediction, but it would produce a more accurate, since there will be more mixing of features, and features are going to be much more refined than having lower by FPN layers. So moving on to the advantages. So over I keep mentioning that the advantages would be speed. So by eliminating the entire region proposal stage, so these models are significantly faster. Um, as Joseph Redmond showed in the original YOLO, it makes real-time detection on a live video feed possible, since uh, I believe uh, the two-stage object detectors would generally perform under 30 FPS, while the initial YOLO architecture would perform at a higher FPS, so which means it's much faster when it comes to doing predictions. Another advantage is simplicity. So the architecture is simpler. It's a single end-to-end network. So this makes it easier to train as well as to optimize. So then overall, the generalizability. So this is quite unique to the single stage object detector, since it's looking at the whole image. So it's Because the network always sees the entire image context for every prediction, it's less likely to make contextual errors. Like for example, uh, it can it's for example mistaking a person in a painting for a real person. So since it's seeing the entire image, it can have a better quote unquote context of the image and uh, can make fewer contextual errors. Then moving on, we have the limitations of single stage detectors. First of all is the localization accuracy. So this is the trade-off between two-stage models with their dedicated refinement stage. It, since two-stage models have a dedicated refinement stage, it is better at getting perfectly tight bounding boxes. So single-stage object detectors are fast, but they're not as accurate as two-stage object detectors. They also struggle with small and crowded objects, since the dense grid-based approach can have trouble when many tiny objects are clustered together. So there have been instances of wherein it is largely solved by multi-scale feature pyramid techniques, uh, as we saw in the SSD and the modern YOLOs. So this is actually something that has been being solved by the latest iterations of different YOLO models. And then last we have is the class imbalance. So this is a massive training problem where the single stage makes thousands of predictions. Single stage detector makes thousands of predictions per image, but some of them can be classified as just background or not really part of the objects that we're trying to detect. So the network can be overwhelmed by all the negative examples. So and uh, another solution that's being proposed to this was the focal loss function, which was introduced in 2017 in the 2017 RetinaNet paper and forced the model to focus on hard to classify examples. So moving on to the use cases. So first we have is the real-time traffic monitoring. So the system is processing a video feed from a highway camera and identifying cars, trucks, buses, all the confidence scores. This kind of real-time analysis is only possible with fast and single-stage detectors, since highway speeds can go up to uh, well, here in the Philippines, it will be a minimum of 60 kilometers per hour. That is not much enough time for cameras to for two-stage object detectors to accurately detect cars, since uh, I believe standard cameras come with either 30 FPS or 60 FPS. So that would mean that it will struggle with real-time detection, but single-stage object detectors would work well, since uh, it's quite faster than two-stage object detectors. This will be also the focus of my workshop, which would be training a dataset of different cars and to a single-stage object detector. So moving on to the next example would be, so this is a part of real-time manufacturing. So this is a high magnification image of a printed circuit board or a PCB. So the red boxes highlights the different defects that the model has been trained to find. So these are things a human inspector might miss, since first of all, these are quite small, since this is magnified and these are solder points that are in the PCB. So th- so these things like missing a hole and mouse bite or an open circuit are things that the inspector might miss. And overall, it's better for automation, since manufacturing lines, these PCBs are mostly mass produced. So having object detectors trained to that are trained to detect defects or anomalies within a production line is also one of its popular use cases. Lastly, we have is security or surveillance. So these models are used for human behavior analysis as well. So the detection model provides all the detection model here in this case provides the important step of finding the people, and then this is actually partnered with another model that can analyze their posts or track their movements. So since since this is done in real time, which means that single stage object detectors would be um, the best use case here, since it's quite faster than two-stage object detectors. So yeah, so majority of use cases for single stage object detectors would be more focused on real-time detections. So that would be all for my lecture. And once again, I'm Matthew Ryan Karandang, and thank you for listening. And here are the references to my lecture.
Thank you, Ryan, for the presentation. I have already received the question for you based on your presentation. So let me read the question for you. Is the BiFPN layer from the efficient net architecture the same as skip connections that we find in UNet? So maybe you can go back to BiFPN. Are these skip connections?
So for skip connections, what we can see here is that from above, we can see that for the skip connections, it would mean that it's not really, how do I say this? Some features from coming from the backbone is not really mixed into the different features that come from different layers. So uh, as we can see here, we there are arrows that are traversing from or skipping different nodes here, which are basically nodes that mix different features together. So while it skips nodes, it goes directly into the prediction head, since the BiFPN layer would like think of it as it doesn't really benefit the model of in if you mix these types of features. So these features are more important in being considered at the final detection head rather than mixing it with different features coming from different layers.
Okay. Maybe to add to that, because I think the question is directly asking whether the BiFPN that we're seeing here, is it considered a skip connection? I think there are parts in the BiFPN architecture that has skip connections. Am I correct, Ryan?
Yes.
That's what you're trying to say no, earlier. Okay.
Yes, po.
But in terms of, I actually view this as a module, the whole BiFPN, this whole BiFPN, I think of it as a module, basically a collection of different layers. So this is just one layer of the BiFPN. And we see that it's composed of different convolution operations. But to maybe answer the question, I would consider this skip connections. Okay, similar to the idea of skip connections in ResNet. And the other thing that I would like to, or how I would answer the question is, I'll be sending a link to everyone in the chat. Maybe Ryan, can you please open the link para we can answer the question fully? Yeah, I would imagine the BiFPN module is inspired by the FPN, the original FPN paper, which is Feature Pyramid Network. I think this is around 20, ayan, according to the archive paper, it's around 2017. Um, The main idea being, so this is the feature pyramid network. Okay. And it's being compared to different types of fusing together different features. Okay. So this is FPN, not by FPN. And I think this is the inspiration of how they did by FPN. So we've seen patterns in computer vision. The first one is letter A, and this one uses different the same image being inputted into the detector using different image sizes. Then they will predict for each image size. So we expect to see the smallest or the smaller objects in the bigger image size, right? So that's the idea behind image pyramid. This one follows your YOLO architecture. Single image resolution, you pass it through a convolution operation, right? And it will give you just one prediction. So whether the object is big, whether the object is small, it will be predicted only here. So this prioritizes speed because you would imagine that option A would have, since you are doing it for multiple image sizes, same image, different sizes, and predicting it multiple times, this would take a lot of time. Okay? So this, on the other hand, is what SSD is doing. You have one input image, so it's a combination of these two. One input image, pass it through convolutions, and for each feature map or for each selected feature maps, you're going to have some predictions. Okay? That's the high level idea. We need more time to be able to flesh out the ideas, but that's the high level idea. This is the input size, it's the one being changed, and you're passing the same image multiple times. But here, one image size, pass it through the convolution layer, and we know the convolution would produce smaller and smaller resolution of the feature maps, or in our computer vision class, we call it templates. So this is template that has a larger resolution. This is a template having a lower resolution, and we're going to give predictions for each feature map or for each template. What FPN does, or feature pyramid network does, is it takes all of these ideas into account, okay, and combines the idea into what it calls a feature pyramid network, which is basically, I would say, so this is the forward pass, same as this. That's why this figure is very good, no, for a figure number one in a paper. So this part is the same. What's the difference going from C to D? So D is the one being introduced in this paper. These are famous people. For those who are taking the computer vision elective class under me, familiar with this name, si Kai Ming He. Also the same person who wrote ResNet. This is from, as I mentioned, Facebook. This is also a famous person in computer vision. I forgot the main contribution of Chung Yilin. This contributed the RCNN, if I'm not mistaken, the RCN architecture. Ayan, sabi ni Aaron, correct. Yeah, RCNN architecture. I forgot, I think ImageNet, if I'm not mistaken. But this part is the one being contributed to us by FPN. Okay, by feature pyramid network. So it does another set of convolutions before you predict. As compared to this one, do one set of convolutions, then predict. Here, do one set of convolutions, do another set of convolution before you predict. That's the high level idea, but maybe we have to sit down and have one full set of lecture just to have more details about what's being shown here. Okay. Now, what is by FPN on the other hand? Can you show it to us, Ryan? I would say on a high level discussion, I would say it's a much more complicated version of FPN or feature pyramid network. That's why it's called um, by FPN or bidirectional feature pyramid network. Looking at this one, it's an improvement of what we saw in FPN, but the main idea is still this part tries to improve the predictions before you actually predict here. Okay. I do appreciate that question. That's a very interesting question for this lecture. Any more questions from the listeners? Maybe you can raise your hand if you have no questions so that we can proceed with the next presenter. Actually, I forgot to, do not lower your hands, please. I forgot to mention earlier, this is more of a news. Okay, maybe I'll lower your hands now. Anyone familiar with the YOLO architecture? I think most of us are familiar with that. Are you familiar with the first version of YOLO? YOLO V1 discussed here. Redmond, Joseph Redmond, he actually stopped doing research after YOLO V3, if I'm not mistaken, YOLO V3. Just a bit of history, because during this time, when he was introducing YOLO, which became YOLO up until now, it's a household name. We're doing our, I was personally doing my MS during this time, my masteral during this time, and I'm working on object detection as well. So he introduced YOLO. By the time he introduced YOLO V3, he stopped doing research. What is his reason? Well, this is in connection to the discussion earlier by Aaron. He mentioned he do not want his research being used in military applications. We're seeing object detection, all of this computer vision research can be applied to military applications, right? So I do not want to contribute towards that. Just a bit of news. I've read this, I think, just this week. I forgot whether it was yesterday or last Monday. But Joseph Redmond is doing research again. I'm not sure if you've seen his website, if you've read his work, but he's a very interesting person, a very interesting writer to read about, because especially if you read the YOLO V3 paper, was a very, it's not an official paper, it's more of a technical report, but the way of writing is a bit comical, if I may say, but the main ideas are there. Okay. He made it a little bit comical, I think, because it's not technically a research paper, although it's still being cited by certain research papers. So if you're intrigued about how he writes, maybe you want to read the YOLO V3 paper. I think I actually do not have any questions about this topic. For those who are taking the elective course this term, this is actually one of the things that we are going to cover in this class. So at least you had a head start of understanding the different developments in object detection. Okay, so I guess if there are no more questions, thank you, Ryan, for the presentation. We really enjoyed it.
Thank you, sir.
Thank you.